Swayam Prabha. Digital India. Educated India.
Now let us go, the next talk is conjugacy and exponential family. Now we saw that many of the operations required for the inference can be conveniently calculated when the distribution is a Gaussian. So it is worth recalling that the points that are desired rate for manipulating the probability distribution in the machine learning context. So there is some closure property when applying the rules of probability, call it as a Bayes theorem. By closure we mean that applying the particular operation returns an object of the same type, and we collect more data and we do not need more parameters to describe the distribution. Since we are interested in learning from data, we want a parameter estimation to behave nicely. So these are all the point you have to remember for manipulating the probability distribution corresponding to machine learning. It turns out that the class of the distribution called exponential family provides the right balance of generality while retaining the favorable computation and inference properties. Before we introduce the exponential family, we have to describe the one example, that is the Bernoulli distribution oriented ideas. The Bernoulli distribution is the distribution for a single binary random variable x with the state x in the interval 0, 1, means tossing a coin 10 times or simultaneously take the 10 coins and toss simultaneously, what have the problem. So this type of the ideas comes, then ultimately we go to the Bernoulli. So it is governed by the single continuous random experiment, and the parameter mu belongs to the closed interval 0, 1 represent the probability x equal to 1, and the Bernoulli distribution BER of mu is defined as P of x over mu equal to mu power x into 1 minus mu whole power 1 by x. So the expectation is mu and the variance is mu of 1 minus mu, where E of x and V of x are the mean and the variance of the binary random variable x. So the right top corner represent the figure, call it as tossing a coin 10 times, and this type of the distribution is called it as a Bernoulli distribution. And below the pictorial representation is a Bernoulli distribution. Take the parameter continuous single parameter continuous mu, start from minus 0.1 to 0.75, that is 0.1, 0.4 and 0.75, and we have a number of observation corresponding to the parameter mu. The values are 0.1, 0.4, 0.75, and we have a number of observation when x equal to 1, and take the value of n equal to 15, that is you take the values of experiments is 15, so that apply in this formula you can get the values of expectation of x and V of x and corresponding mean and variance of the probability of x over mu is called as Bernoulli distribution. Now we have a note and rewriting the above Bernoulli distribution, and where we use the Boolean variables as a numerical value 0 and 1 and express them in the exponents. So it is a trick that is often used in machine learning textbook. Another occurrence of this when expressing the multinomial distribution also mentioned. Now, we have an example of a binomial distribution, that is, a binomial distribution is a generalization of Bernoulli distribution to the distribution over integer, and then they illustrated in the figure 6.10. This represent the Bernoulli distribution, and then we have a what a binomial can be expressed in the description of the probability observation of m occurrences when x equal to 1 in the set capital N, and samples from a Bernoulli distribution is probability of x equal to 1 equal to mu, and a binomial distribution is bin of n comma mu is defined as probability of m by n equal to comma mu is NCM into mu power m into 1 minus mu whole power n minus m. Previously what we have taken that n equal to 15. So, n equal to 15 substitute here, and then you have a mu equal to 1.1 and substitute here, and 1 minus 0.1 into whole power 15 minus m. M stands for corresponding number of possibilities of 0, 1, 0.1, 0.2, 0.3 you have to substitute, so that you have the value of NCM mu power m 1 minus mu whole power n minus m will come, where E of m is a mean into n, here V of m is a n into mu of 1 minus mu. So, here E of m and V of m are the mean and variance of m respectively. So, it is more interesting that simultaneously n numbers distributed, how to find the probability using this distribution, you may get the possibilities of the probability can get it. So, an example where the binomial could be used if we want to describe the probability of observation m heads in capital N coin flip experiments if the probability for observing head in a single experiment is mu. So, for example, you take a beta distribution. So, we may wish to model a continuous random variable on a finite interval. So, the beta distribution is a distribution over a continuous random variable where mu belongs to closed interval 0, 1, and it is often used to represent the probability of the some binary event, and we take the parameter governing the Bernoulli distribution. So, the beta of alpha comma beta, I hope all of you know that beta and gamma function. So, gamma n is equal to integral 0 to infinity e power minus x into x power n minus 1 into dx, and then we have a beta function. So, beta f function is gamma m into gamma n by gamma of m plus n, and the same way here we have a what a distribution beta of alpha comma beta, and illustrated in the following figure 6.11. So, it represent the beta function and corresponding to gamma function here described. So, the governing point of the two parameter alpha is positive and beta is positive. So, we have a definition corresponding to beta function in terms of the probability is p of mu by alpha comma beta is equal to gamma of alpha plus beta by gamma alpha gamma beta into mu power alpha minus 1 into 1 minus mu whole power beta minus 1, and expectation of mu is mean of this value is alpha by alpha plus beta, and the variance is equal to alpha beta by alpha plus beta the whole square into alpha plus beta plus 1. So, more interesting one, the parameter governing the Bernoulli distribution, and this distribution is a continuous random variable as well as continuous random variable over 0, 1. And we have a gamma function is gamma t is equal to integral 0 to infinity x power t minus 1 into exponential power of minus x dx, where t is positive, gamma of t plus 1 equal to t gamma t, right. So, these are all the properties of gamma function we have to use, and note that the fraction of gamma function is normalizes to beta distribution. So, from this example, the beta distribution for different values of alpha and beta, you choose alpha equal to 0.5 and beta equal to 0.5 in the above formula, and then the value is corresponding to blue color represent the expression of the probability of mu by, that is probability of what mu by alpha is 0.5 comma beta is 0.5, so that this blue color represent corresponding nature of the curve of the beta distribution. Suppose alpha equal to 1 and beta equal to 1, then p of mu comma 1, then we have a corresponding color of orange is represent, it becomes a straight line from the point that is 1 to 1. So, this represent the corresponding function, and suppose p that is suppose alpha equal to 2 and beta equal to 0.3, then the probability of mu by 2 comma 0.3 is equal to the representation substituted in the previous definition, so that we have green color represent the nature of the curve start from the 0 to end with the maximum of 0.9 and it touches with the 1. So, this represent, and when alpha equal to 4 and beta equal to 10, then the probability of mu by 4 comma beta is 10. So, this represent the rose color, so corresponding to the start from origin and end up and bend it with and the reaches to 1. So, that is the nature of the Bernoulli function, and when alpha equal to 5 and beta equal to 1, so the probability of mu by 5 comma 1 is equal to that this color represent the corresponding the Bernoulli distribution function. So, in this way we can do the technique of finding the probability distribution from alpha to beta. So, these are all the things we can easily analyze from the formula. Now, the intuitively alpha moves probability mass towards 1, whereas beta moves probability mass towards 0. So, there are some special cases and explained in the Murphy in the year of 2012. For alpha and beta are equal, we obtain the uniform distribution function. If alpha and beta are less than 1, we get the bimodal distribution with the spikes at 0 and 1. If alpha and beta is greater than 1, the distribution is unimodal. If alpha and beta is greater than 1 and alpha equal to beta, the distribution is unimodal and symmetric and centered in the interval 0 comma 1. So, the model by mean is at off. Note, there is a whole zoo of distribution with names, and they are related in a different ways to each other. The Leamis and McQuiston described about that the distribution, and then it is worth keeping in mind that each named distribution is created for a particular reason, but may have other applications. Knowing the reason beyond the creation of the particular distribution often allows insight into the how to the best to use it. Now, we introduced preceding 3 distribution to be able to illustrate the concept of conjugacy. and exponential families. Now, let us go with conjugacy. According to Bayes' theorem, the posterior is proportional to the product of the prior and the likelihood. So, the specification of the prior can be tricky for two reasons. First, the prior should encapsulate our knowledge about the problem before we see any data. So, this is often difficult to describe. Second, it is often not possible to compute the posterior distribution analytically. However, there are some priors that are computationally convenient, that is called it as conjugate priors. Now, we have a definition of conjugate prior. A prior is a conjugate for the likelihood function if the posterior is of the type as a prior. Note, when considering the geometry of probability distribution, conjugate priors retain the same distance structure as the likelihood of described in the Agarwal and Dayum in 2010. So, then we can understand what is the meaning of conjugacy. Now, let us go to the example of beta binomial conjugacy. Consider the binomial random variable x of maps to bin of n comma mu, where probability of x by n comma mu equal to ncx into mu power x into 1 minus mu whole power n minus x, where x varies from 1 to n is the probability of finding x times. So, the outcome heads in capital N coin flips, where mu is the probability of head. So, we place a beta prior on the parameter mu, that is mu is equivalent to beta of alpha comma beta, where probability of mu by alpha comma beta equal to gamma of alpha plus beta by gamma alpha into gamma beta into mu power alpha minus 1 into 1 minus mu whole power beta minus 1. So, if we now observe some outcome x equal to h, that is we see h heads in capital N coin flips. So, we compute the posterior distribution on mu as probability of x by x equal to h comma n comma alpha comma beta, and is equivalent to probability of proportional to probability of x by n comma mu and probability of mu by alpha comma beta, and is proportional to mu power h of 1 minus mu whole power n minus h and mu power alpha minus 1 into 1 minus mu whole power p beta minus 1. After simplifying, it is equivalent to combined together of all the mu power h power alpha minus 1 into 1 minus mu whole power n minus h and 1 minus mu whole power beta minus 1, base are equal, add powers. So, n minus h plus beta minus 1. So, it represents beta of h plus alpha comma n minus h plus beta. So, this is the posterior distribution is a beta distribution as a prior. So, the beta prior is a conjugate for the parameter mu in the binomial likelihood function. Now, we have a table and discussing the common likelihood function, that is likelihood, conjugate prior and posterior. So, if you start with the likelihood is Bernoulli, apply the conjugate prior beta and posterior also beta will come. If you take likelihood is a binomial, so conjugate prior is beta and posterior also beta. If the likelihood is Gaussian, then conjugate is either Gaussian or inverse Gaussian, inverse gamma, and posterior is Gaussian and inverse gamma. Suppose if your likelihood is Gaussian and sometimes Gaussian prior is Gaussian or inverse Wishart and posterior is Gaussian or inverse Wishart. If you take likelihood is a multinomial, then the Gaussian prior is a Dirac-Let and posterior is also Dirac-Let. So, this way we have a example of conjugate priors for common likelihood functions. So, let us start with some beta Bernoulli conjugacy. One example, let x belongs to the interval 0 comma 1 be distributed according to the Bernoulli distribution with the parameter theta in closed interval 0 comma 1, that is probability of x equal to 1 over theta equal to theta. This called this can also be expressed as probability of x over theta equal to theta power x into 1 minus theta whole power 1 minus x. One is success, another is failure based on the Bernoulli we have to relate. So, let theta be the distributed according to the beta distribution with parameter is alpha comma beta, that is probability of theta over alpha comma beta is directly proportional to theta power alpha minus 1 into 1 minus theta whole power beta minus 1. So, multiplying the beta and the Bernoulli distribution, we get probability of theta over x comma alpha comma beta is proportional to probability of x over theta into probability of theta over alpha comma beta. Now, we have the formula, probability of x over theta is theta power x into 1 minus theta whole power 1 minus x, and probability of theta by alpha comma beta is theta power alpha minus 1 into 1 minus theta whole power beta minus 1, which is equal to theta power base equal theta power alpha plus x minus 1 into 1 minus theta whole power beta plus 1 minus x minus 1, because base are equal, add power, and this represent the probability of theta over alpha plus x comma beta plus 1 minus x. So, this last line is a beta distribution with the parameter alpha plus x and beta plus of 1 minus x. So, this expression is represented by beta Bernoulli conjugacy. Now, we have a sufficient statistics. Recall that statistic of a random variable is a deterministic function of a random variable. For example, x equal to x1, x2 and so on xn is a vector of the univariate Gaussian random variable. Then x is approaches to capital N of mu comma sigma square. Then the sample mean mu is equal to 1 by n of x1, x2 and so on xn is a statistic. So, the Ronald Fisher discovered the notion of the sufficient statistics. So, the idea that there are a statistics that will contain all available information that can be inferred from data corresponding to the distribution under consideration. In other words, sufficient statistics carry all the information needed to make inference about the population, that is, there are the statistics that are sufficient to represent the distribution. So, this is called it as sufficient statistics. Next we have a theorem, Fisher-Neyman. So, according to the theorem, Legman and Kessel law in the year of 1998 and found out that let x have a probability density function of p of x over theta, then the statistics phi of x are sufficient for theta if and only if phi of x over theta can be written in the form of p of x over theta equal to h of x into g of theta of phi of x. So, h of x is a distribution independent of theta and g suffix theta capture all the dependence on theta through sufficient statistics phi of x. So, this is the statement designed by the Fisher-Neyman, and then p of x over theta does not depend on theta, then phi of x is a trivially a sufficient statistics for any function phi. So, the more interesting case is that p of x over theta is dependent only on phi of x and not x itself. So, in this case phi of x is a sufficient statistics for theta. So, in machine learning we consider the finite number of samples from a distribution. One could imagine that for a simple distribution we only need a small number of samples to estimate the parameters of the distribution. So, we could also consider opposite problem. If we have a set of data that is sample from an unknown distribution, which distribution gives the best fit? So, a natural question to ask this, as we observe more data, do we need more parameter theta to describe the distribution? So, it turns out that the answer is yes in general, and this is studied in non-parametric statistics. A converse question is to consider which class of distribution have a finite dimensional sufficient statistics. So, that is the number of parameters needed to describe them does not increase arbitrarily. So, the answer is exponentially family distribution and described the following section. So, next we are going to describe the exponential family. There are three possible levels of abstraction. We can have when consideration distribution, either discrete or continuous random variable. At the level 1, the most concrete end of the spectrum, we have a particular named distribution with the fixed parameters. For example, univariate Gaussian distribution n of 0, 1 with 0 mean and a unit variance. So, in machine learning, we often use the second level of abstraction, that is, we fix the parametric form and infer the parameters from data. For example, we assume univariate Gaussian n of mu comma sigma square with the unknown mean mu and unknown variance sigma square, and use the maximum likelihood fit to determine the best parameter mu of sigma square. So, we will see an example of when this condition is holds good like that. So, next we have a remark, a brief historical anecdote. Like many concepts in mathematics and science, exponential families were independently discovered at the same time by different researchers. In the years 1935 to 36, Edwin Pitman in Tasmania, George Darmos in Paris and Bernard Koopman in New York independently showed that the exponential families are the only family that enjoy the finite dimensional sufficient statistics under repeated independent sampling. So, an exponential family is a family of a probability distribution parameterized by theta belongs to r power d of the form p of x over theta equal to h of x in the exponential of inner product theta comma phi of x minus a theta of inner product, where phi of x is a vector of sufficient statistics. In general, any inner product can be used in the equation 107, and for concreteness we will use the standard dot product inner product as theta comma phi of x equal to theta power, that is conjugate theta power t is represent the conjugate of phi of x. So, note that the form of the exponential family is essentially a particular expression of g theta of phi of x is the Fisher-Neyman theorem. So, the factor h of x can be observed into dot product term by adding another entry log of h of x to the vector of the sufficient statistics phi of x and constraining the corresponding parameter theta suffix 0 equal to 1. The term a of theta is the normalization constant that ensures that the distribution sums up or integrates to 1 and is called log partition functions. So, a good intuitive not a consideration of this one, and if you have a consider the exponential family as a distribution of the form, then p of x over theta is equal to proportional to exponential of theta conjugates into phi of x. So, for this form of parameterization, the parameters theta are called natural parameters. First glance, it seems that exponential families are a mundane transformation by adding the exponential function to the result of a dot product. However, there are many implications that allow for convenient modeling and efficient computation based on the fact that we can capture the information about data in phi of x. Next, we will discuss the Gaussian as an exponential family. Consider the univariate Gaussian distribution n of mu comma sigma square. Let phi of x equal to x comma x square. Then by using the definition of exponential family, p of x over theta is proportional to exponential of theta 1 x plus theta 2 x square. Setting theta is mu by sigma square comma minus 1 by 2 sigma square of conjugate. and substituting this into equation 109, we obtain P of x over theta is proportional to exponential of mu x by sigma square minus x square by 2 sigma square, and further it is proportional to exponential of minus 1 by 2 sigma square of x minus mu the whole square. So, therefore, the univariate Gaussian distribution is a member of exponential family with the sufficient statistics phi of x equal to x comma x square and have the natural parameters given by theta in the equation 110. Now, we have an example. Start with the Bernoulli as exponential family. Recall Bernoulli distribution from the example 6.8 already we discussed, and probability of x by mu is nothing but mu power x into 1 minus mu whole power 1 minus x, where x belongs to 0 comma 1. Now, this can be written in the exponential family form. P of x by mu is equal to exponential of log. Exponential log can cancel, therefore, we have to what adjust like that. So, mu of x into 1 minus mu into 1 minus x. Now, log of a b equal to log a plus log b. Therefore, log of mu x equal to x log mu, and log of 1 minus mu whole power 1 minus x is 1 minus x into log of 1 minus mu, because log of m power n equal to n log m. So, that technique you have to use it, and then we have the simplification exponential of x into log mu, and we splitted into this 1 into log of 1 minus mu here, minus x into log of 1 minus mu here, and combined these together, and we have a x into log of x log mu minus x log of 1 minus mu is equal to x, take it outside. Therefore, x into log a minus log b equal to x into log of a by b plus log of 1 minus mu. So, this Bernoulli can be expressed as an exponential family. So, the last line of 113D is identify the exponential family, and by observing that h of x equal to 1. Here theta is equal to log of mu by 1 minus mu, and phi of x equal to x, and a of theta equal to minus log of 1 minus mu. So, this can be expressed as log of 1 plus exponential of theta. So, the relationship between the theta and mu is invertible. So, mu equal to 1 by 1 plus exponential of minus theta. So, the equation 118 is used to obtain the right equality of 117, because a of theta is equal to log, taking anti-log and then corresponding mu you can get it. So, we have a note. So, the relationship between the original Bernoulli parameter mu and the natural parameter theta is known as the sigmoid or logistic function. We observe that mu in belongs to 0 comma 1, but theta in R. Therefore, the sigmoid function squeezes a real value into the range of 0 comma 1. So, this property is useful in machine learning. For example, it is used in logistic regression as well as nonlinear activation function in neural network distribution. Consider the random variable x is a member of the exponential family. P of x over theta equal to h of x into exponential of inner product theta comma phi of x minus a of theta. So, every member of the exponential family has a conjugate prior. Therefore, P of theta over nu is equal to h of theta over c exponential of r1 nu 2 comma theta comma minus a of theta minus ac of nu, where nu equal to nu 1 nu 2 has the dimension of theta plus 1. So, the sufficient statistics of conjugate prior are theta comma minus a theta. By using the knowledge of general form of the conjugate priors for exponential families, we can derive the functional forms of the conjugate priors corresponding to the particular distribution. Now, we have an example. So, recall the exponential family form of the Bernoulli distribution P of x by mu is exponential of x log of mu by 1 minus mu plus log of 1 minus mu. Now, the canonical conjugate prior has the form P of mu by alpha comma beta is equal to mu by 1 minus mu of exponential of alpha log of mu by 1 minus mu plus beta plus 1 into log of 1 minus mu minus AC of nu. So, here nu is equal to alpha comma beta plus alpha whole transpose and HC of mu equal to mu by 1 minus mu. So, the equation 1.2 simplify to P of mu by alpha comma beta equal to exponential of alpha minus 1 into log mu plus beta minus 1 into log of 1 minus mu minus AC of alpha comma beta. So, putting this in non-exponential family form yields probability of mu by alpha comma beta is proportional to mu power alpha minus 1 of 1 minus mu whole power beta minus 1. So, which we identify as a beta distribution. So, in the example 6.12 we assumed that beta distribution is a conjugate prior of the Bernoulli distribution and it showed that it was indeed the conjugate prior. In this example we derived the form of the beta distribution by looking at the canonical conjugate prior of the Bernoulli distribution in exponential family form. Now, change of variable or inverse transform. For example, assuming x is a random variable distribution according to the univariate normal distribution n of 0 comma 1. So, what is the distribution of x square? Another example which is quite common in machine learning is given that x1 x2 are a univariate standard normal, what is the distribution of half into x1 plus x2? So, the one option to work out the distribution of 1 by 2 into x1 plus x2 is to calculate the mean and variance of x1 and x2 and then combine them. So, as we saw the section, we can calculate the mean and variance of resulting random variable when we consider the affine transformation of the random variable. However, we may not able to obtain the functional form of the distribution under transformation. Furthermore, we may be interested in nonlinear transformation of random variable for which the closed form expression are not readily available. So, we have a note in this section, we will explicit about the random variables and the values they take. Hence, we recall that we use the capital letter x and y to denote a random variable and small letters x comma y to denote the values in the target space T that the random variables take. We will explicitly write the PMF, probability mass function of a discrete random variable x, as P of x equal to x. For continuous random variable x, the probability density function is written as f of x and the cumulative density function is written as capital F of x over x. So, this transformation is a discrete random variable can be understood directly. Suppose there is a discrete random variable x with probability mass function p of x equal to x and invertible function u of x. Consider the transformed random variable y equal to u of x with probability mass function p of y equal to y, then probability of y equal to probability of u of x equal to y. So, this transformation is interest and the inverse is x equal to u inverse of y. So, this way we can find the inverse of this where we can observe that x equal to u inverse of y. For a discrete random variable, I directly change to the individual events with the probability approximately transformed. Now, the distribution function technique goes back to the first principle and using the cumulative density function and the fact that differential of the PDF. So, if you do the differential of this one, we have a probability density function will come. For a random variable x and a function, we find the PDF, probability density function random variable y equal to u of x by finding the CDF is fi of y equal to p of y less than or equal to y, and differentiating the CDF fi of y to get the PDF of f of y is d by dy of fi of y. So, we also need to keep in mind that the domain of the random variable may have changed due to the transformation by u. So, let us go one example. Let x be a continuous random variable with the probability density function on 0 less than or equal to x less than or equal to 1, f of x is given 3x square. We are interested to find the probability density function y equal to x square. Now, the function f is an increasing function of x because it is a continuous, and therefore, the resulting values of y lies in the interval 0, 1. So, we obtain fi of y equal to probability of capital Y less than or equal to y by the definition of CDF, and then replace y equal to x square and then x square less than y, and by inverse x is less than or equal to y power half. So, it reduces to definition of the CDF of f over x of y power half. By definition of a CDF, we have a integral 0 to the range 0 to y power half of the function is 3x square. So, 3t square into dt will come, and then integrate it 3 into d cube by 3 and over the limit 0 to y power half, and then the value is 3 get cancelled, y power 3 by 2 will come. So, f over y of y is y power 3 by 2. So, this is the result of the integration. Therefore, the CDF of y is what? Fi of y is equal to y power 3 by 2. So, the range of y is lies between 0 to 1. If you want that PDF, probability density function, simply differentiate of CDF. So, the d by dy of fi of y, that is differentiate with respect to y. So, 3 by 2 into y power 3 by 2 minus 1. So, 3 by 2 into y power 3 by 2 minus 1, which is equal to 3 by 2 into y power what? Half. So, that is the meaning of what? PDF from the CDF. So, this way we can calculate the CDF and PDF. So, that is the real application corresponding to the given formula. Now, in continuation of the probability density function, cumulative density function, let us go with change of variables. So, the distribution function techniques in the section is derived from the first principles based on the definition of CDFs and using the properties of inverses, differentiation and integration. So, this argument from the first principle relies on two facts. One, we can transform the CDF of y into an expression that is CDF of x. Second, we can differentiate the CDF to obtain the PDF. So, we have a note. The name change of variables comes from the idea of changing the variable of integration when faced with the difficult integral. For univariate functions, we use the substitution rule of the integral f of g of x into g dash of x into dx equal to f of u into du, where u equal to g of x. So, the derivation of this rule is based on the chain rule of the calculus, and by applying twice the fundamental theorem of calculus. So, the fundamental theorem of calculus formalizes the fact that integration and differentiation are somehow inverses of each other. So, an intuitive understanding of the rule can be obtained by thinking loosely about the small changes to the equation u equal to g of x. So, that is by considering delta u equal to g dash of x into delta x as a differential of u equal to g of x. By substituting u equal to g of x, the argument inside the differential of u equal to g of x. By substituting u equal to g of x, the argument inside the integral on the right side of the equation 133 becomes f of g of x. So, by pretending that the terms of du can be approximated by du is approximately equal to delta u, which is equal to g dash of delta x, and that delta x approximately capital delta x. So, consider the univariate random variable x and it is invertible function u which gives us another random variable y equal to u of x. Now we assume the random variable x states that x in a comma b by the definition of CDF. So we have fy of y equal to probability of y less than or equal to y. So we are interested in a function u of the random variable probability of y less than or equal to y equal to probability of u of x less than or equal to y. So we assume that the function u is invertible. So an invertible function on interval is either strictly increasing or strictly decreasing. So in the case that u is strictly increasing, then its inverse is also strictly increasing. So by applying the inverse, the argument p of u of x less than or equal to y, we obtain p of u of x less than or equal to y is nothing but p of u inverse of u of x less than or equal to u inverse of y, which is equal to probability of x less than or equal to u inverse of y. So the rightmost term is an expression of the CDF, and the definition of CDF in terms of the PDF is probability of x less than or equal to u inverse of y equal to integral a to u inverse of y of f of x. So we have an expression of the cumulative density function of y in terms of x. So f of y over y equal to integral a to u inverse of y of f of x dx. So to obtain the PDF, we differentiate with respect to y of f of y equal to d by dy of fy of y, which is equal to d by dy of integral a to u inverse of y f of x dx. So note that the integral on the right hand side is with respect to x, but we need an integral with respect to y because we are differentiating with respect to y. In particular, we get the substitution f of u inverse y into u inverse dash of y dy equal to f of x dx, where x equal to u inverse of y. So in the equation 140 on the right hand side is fy equal to d by dy of integral a to u inverse y of fx u inverse y of u inverse dash of y dy. So we recall that differentiation is a linear operator, and we use the subscript x to remind ourselves for f of x into u inverse of y is a function of x and not y. Therefore, the fundamental theorem of the calculus again fy equal to fx of u inverse of y into d by dy of u inverse of y. So we have to recall for assume that u is a strictly increasing function. For decreasing function, it turns out that we have a negative sign. When we follow the same derivation, we introduce absolute value of the differential to have the same expression for the both increasing and decreasing u. So f of y equal to fx of u inverse of y into modulus of d by dy of u inverse of y. So this is called it as change of variable techniques. So the term d by dy of u inverse of y measures how much a unit volume changes when applying u. So we have a note, the comparison to the discrete case, we have an additional factor of modulus of d by dy of u inverse of y. So the continuous case requires more care because probability of y equal to 0 for all y. Therefore, the probability density function f of y does not have a description as a probability of an event involving y. So these are all the things you have to remember of probability density function, where it does not have a description, where it has a description, that we have to know. Based on that, we have a theorem. Let f of x be the value of the probability density of a multivariate continuous random variable x. If the vector valued function y equal to u of x is differentiable and invertible for all values within the domain of x, then for corresponding values of y, the probability density of capital Y u of x is given by fy equal to fx of u inverse of y into determinant of dou by dou y of u inverse of y. For example, consider bivariate random variable x with the states x equal to x1 x2 and a probability density function f of x1 x2 equal to 1 by 2 pi into exponential of minus 1 by 2 x1 x2 transpose of x1 x2. So we use the change of variable techniques from the theorem 6.16 to derive the effect of the linear transformation of the random variable. consider matrix A in R power 2 cross 2 defined as A equal to A, B, C, D. So, we are interested in finding the probability density function of the transformed bivariate random variable with states y equal to x. Now, we know the recalling of the change of variable, the inverse transform x as given by y. Since we consider the linear transformation, the inverse transformation is given by the matrix inverse for 2 cross 2 matrix. We can explicitly write out the formula given by x1 x2 equal to A inverse of y1 y2 equal to 1 by AD minus BC of change the place and change the sign of the opposite diagonals into y1 y2, so that you can get the corresponding explicit value of the given function. So, observe that AD minus BC is a determinant of A and corresponding probability density function is given by f of x equal to f of A inverse y, which is equal to 1 by 2 pi of exponential of minus 1 by 2 y transpose into A minus transpose into A inverse into y. So, the partial derivative of the matrix times a vector with respect to the vector is a matrix itself. Therefore, dou by dou A of A inverse y equal to what? Dou by dou A of y is 1, therefore, A inverse will come, and the determinant of the inverse of the determinant. So, the determinant of the Jacobian matrix is determinant of dou by dou A of A inverse y, which is equal to A inverse, and we have the value of 1 by AD minus BC. Now, we apply the change of variable formula. So, the theorem by multiplying the equation 1.48 and 1.50, so that f of x equal to modulus of determinant of dou by dou A of A inverse y, so which is equal to 1 by 2 pi into exponential of minus y by 1 by 2 into y transpose A power minus t into A inverse of y into AD minus BC whole inverse. So, we have a note in this section, the density f of x in the equation 148 is actually the standard distribution of the Gaussian, and the transformed density f of y is a bivariate Gaussian, and the covariance is denoted by summation equal to A transpose.